Okay, let's go through my linear algebra collection. This is just my correction for that. So my actual thing is not, this is not my actual paper. This is just the actual paper, but not my response to it. My response is on another sheet. This is redone. Okay, so let's go with question one. We are first given a two n times n matrix A and B are said to commute if A B equals BA, so it doesn't matter the order. So in part A, we have A is equal to this matrix, find a matrix B that A, B do not commute. Okay, so this is just basically easy points. So we just write A here and we set B to be just A, B, C, D. And then we just multiply it together. We know that AB gets to this form, BA gets to that form. To make AB not equal to BA, we just set them to be different. So we can get B is equal to this form. B is equal to this. And we have our counterexample. So that's two easy free marks. And then in part B, we have suppose any two matrices in the set S from A1 to AM commute. Show that any two matrices in the span S commute. Recall that S is a set of all linear combinations of elements of S. Okay, so if I have this, I just suppose that I just go with my conditions. S is equal to this, and it commutes. I want to show that it does indeed commute. So I know that I start off anything that AI AJ is equal to AJ AI because I'm given that it commutes. So inside the span is the definition of basically the linear combination of anything in S. So then let's say that for X and Y, which are arbitrary matrices that are in the span, in the set of S, then we just set Ci and Di Tj to be like linear combinations of their coefficients. And then we could get the form of xy is equal to these two things multiplied together. So then we can get just organized together, we get this form. Since we know that AI and AJ commute and C and D are coefficients, so we can move them in any way we want, we just rearrange it to be of this form. And that means that it's y times x, so we show that it is commutative. And that the whole thing, because x and y are arbitrary, we know that it holds for anything inside this. So we showed this successfully. Okay, so part C, let's see what it asks. So now we're given additional info that if in the form of a 4 times 4 matrix of C, A, B, C, D, it's in this form. So everything's like kind of like a diagonally, like stripped. And now we have A, B, C, D is inside R, it's called circulant. Okay, so that's a new definition. Part C asks to show that the circular matrices form a subspace of the vector space of 4 times 4 matrices. Okay, so we're just trying to show subspace. Subspace is pretty standardized. This is bookwork. We just want to show first it includes zero, then it's closed under addition, and it's closed under scalar multiplication. So we do exactly that. So we first define our thing, let W equal the set of circular matrices C, A, B, C, D. When A, B, C, D is equal to zero, so our zero case, we see that C000 is indeed inside our W, which is a circular matrix. Okay, now we want to show closed under addition. So we set M1 to be equal to C of, let's just call A1, B1, C1, D1, and M2 to be with the twos. So we know that M1 plus M2 is just basically equal to C, each of the coefficients when we add it together, we see that it's just basically A1 plus A2, B1 plus B2, so on and so forth. So then that means that the sum is still ultimately still a circular matrix. So it's under closed under addition because we can write it in this form. And it's the same story with the scalar multiplication because for, let's say, any constant k that's not equal to zero, um, even zero is included because we already talked about that case. We have k times m1 is just basically equal to k of a, B, C, D. And then if we put the k into each of the thing, we're going to get k, A, K, B, K something. So then we can just rewrite it in this form. C of K, A, K, B, K, C, K, D. So that's still a circular form, so it's closed under scalar multiplication. Since it's both zero, closed under addition and closed under scalar multiplications, all conditions satisfy, and we have a subspace. Okay, let's check part D. State the dimension of the subspace and provide a basis. No proof required. Okay, so it's 2 marks, so we don't really have to do that much work for this. We just need to get a dimension of the subspace and provide a basis. We already mostly got our things. So like we know that okay, if we have we see that on the diagonals it works out. The circular matrix has A, B, C, D, 4 parameters. Great, it's already set up in this form. We just have our first basis, second basis, third basis, fourth basis. Very straightforward. And because we have 4 bases, our dimension is 4. This is like an easy point gainer. In part E, we have find C01100, um, yeah, to the ith power. So we want just basically this thing times itself by I times. So then we kind of go back to like just doing it because we see that it's a lot of one, so it's not going to increment but it's not going to like when you multiply something, if it's like, let's say powers of two, then it would increase exponentially. Whereas inside here, because it's one, like it's not going to get bigger in any way. So we just try it out and we just see that in the first one, when I equals 1, we get this form. When I is equal to 2, we get to this. 3 is this. 4 is this. And when we times it once more by this matrix, we get back to this form. So we see there's a pattern that it repeats by 4. So then whichever we just modulo by 4 and whichever it is whichever form it is. So it's just basically checking what the coefficient of the exponent is and modulo that by and finding the modulo and we just see whichever it is. And let's see part F. Um Use part B and possibly other parts to show that circular matrices commute. So this one is definitely like a bigger question in question 1. So we do want to show that okay, so how we do this is let's say we have our C, A, B, C, D using part E. We can say that earlier we have um, the C matrix is composed of each of the matrix from 1, 2, 3, 4, each of the things with 1 in each place, right? So then that means that is basically um, A times of I, which is in that first one. And then we do have the next one because we know that it shifts from part E. Each of the matrices is just shifted. So then we have B times J plus C times J squared times D times J cubed. So that was the conclusion we got from part E. And we know that our basis is S, which is just 1 J squared, J cubed. So then we know that the powers of a single matrix always commute with each other. Since S commutes pairwise instead of circular matrix is the span of S, then by B they must commute. So it's like a pretty straightforward logic reasoning. I think the major difficulty with part F is kind of seeing using part B, you know you have to use it because the question gave it to you. But part E is like just seeing that you can rewrite each of them with this form like BJ, CJ squared, just seeing that you can be like what is it called, shifted over with the part from E is a little slightly challenging, but because we just did that part earlier, I think it's definitely doable. And then part G is also a bigger question because it's 4 marks. Compute the eigenvalues of C0, 1, 0, 0. What can you conclude about the eigenvectors of circular matrices? Okay, so the second part was difficult. I'll explain why, because I didn't know that before going into this. But I guess it's after doing it, I did learn. It's kind of just like a definition. You kind of know it or you kind of don't, sort of thing. So we have this is our matrix. If we're trying to find eigenvalues, that's pretty straight standardized because we're gonna be trying to find the determinant, the characteristic equation, the typical way. So we do have determinant of j minus lambda I is equal to 0. And we have on the diagonal, we have this all of the negative lambda from this part, and then the rest of the matrix is here. And then we set that to be equal to 0. And then because it's a 4 times 4 matrix, it's kind of difficult for us to have a straight formula to solve it. So we would use either cofactor or Laplace. And because we have a bunch of zeros here, I think Laplace would be a much better thing. And we can just apply that in column one. So we apply it inside this column. Okay, in blue. Sorry, that was a little not very nice. Okay, so what we do is we uh, take the first one, which is positive, like inside this checker square, because I and j are both ones. So then it's positive. Then we have negative lambda times whatever that remains in this box. And that's that. And then we have 0, 0, which don't create anything. And then this one's positive, negative, positive, negative. So this one's negative. So it's negative 1 times whatever remains inside this square up here. That's not in that row. Okay, it's kind of messy now, but you get the idea. So you have this matrix, the thing inside the column times the whatever matrix that remains. That's not excluding the row and column of that. And we see here that it's a pretty nice pattern we get. We see, okay, great, we have a triangular form. So that makes our calculation very, very simple, and we're very happy to see that. So on this, because we see it's an upper triangular, we can just get the determinant by doing the diagonals, and similar story with the lower triangular. And what we can do is in the front, we get negative lambda times this is negative lambda cubed minus 1 times 1 cubed. So we get this expression. So this is our characteristic equation, and we know that's equal to 0. So then we get our four roots, which are plus minus 1 plus minus I. And then the last part about this question that was asking, what can you conclude about eigenvectors of circular matrices? So the thing when we inside here is that since circular matrices commute, they are simultaneously diagonizable. So that's what they're looking for. The answer they're looking for is simultaneously diagonizable. So basically, what this term means is that there exists a unique common basis of eigenvectors for all circular matrices. So the inside here, because we see that they share like the same basis of like the four things, right? So then they should share the same eigenvectors. So that's what they mean by that. But I think this question is kind of like, okay, that's not something very intuitive. So like you sort of know it or you sort of don't. Okay, moving on to the second question. Define a sequence of numbers L0, L1 as follows. So this is kind of like a typical recurrence question of like, kind of looks like Fibonacci to me, except it's a different number. L0 is defined to be 2, L1 is 1, Ln is Ln minus 1, Ln minus 2 for n greater than or equal to 2. So then they give us an example, we just add it up, we get that. So find a matrix A such that A of this is equal to that, holds for all n greater than or equal to this, prove this property. Okay, this is pretty standardized. So we do want something of this form is equal to that. So we just put in the definition of Ln plus 1 is just Ln plus Ln minus 1. This is pretty straightforward. So this is just an addition. If we want addition to happen, we just set A to be 1, 1, 1, 0, so that we make sure that the addition happens when we do the matrix multiplication. So part A is pretty standardized, I'd say. Part B, use the previous part to show that A to the n power 1, 2 is equal to Ln plus 1, Ln holds for all n greater than or equal to 0. So this is like where most of us fell into a trap of just like doing the question straight off by pattern. So like what I did at the time, and even in the correction, is I just wrote an 1, 2 is equal to this. This is what I want to show. I know that L1, L0 is equal to 1, 2. So then I just plug it in so that Vn is equal to A, Vn minus 1, and then I do Vn minus 1. I can do that again, just a recurrence formula, plugging that in. And then after plugging it in n times, then I would get to the V0 part. And my V0 part is the 1, 2. So that I would just be able to get to this form of what I need. So I see the pattern pretty clearly because I substitute the recurrence in every time. But most of us lost half of the marks for this question because this is not a very rigorous proof. Like this is not a rigorous proof. It's just more of like a pattern spotting. So then once we see this pattern, it should be what we should do is use induction to say that okay, we see that it's this, so then we can just prove it that way. That's true. So we work backwards, kind of induct rather than recurse. Okay, let's go to question C. Compute the positive eigenvalue of this of A. Show that the other eigenvalue is this. Okay, so the golden ratio shows up. Awesome. So we have our A, pretty straightforward. Eigenvalue is pretty standardized at this point. Determinant A minus lambda I. Plug this in, get our characteristic equation. We find that it's 1 plus minus square root of 5 divided by 2. And it asks us to take one more step to show that it's 1 over, yeah, negative 1 over that thing. So that if it's negative 1 over that thing, I just put this in and see where that takes me. Put this in. After some algebra, I do indeed get the other with the negative side of the golden ratio. So that's pretty straightforward, that question. And then part D, this is the part I struggled quite a lot on. Like during the thing, I forgot how to calculate for eigenvector. I got the equation, but somehow I just didn't solve it. So a trick in this question part D is definitely not plugging in the golden ratio directly, but just writing it as a symbol. And also keeping in mind that using this property that negative 1 divided by the golden ratio is the other eigenvector. So you can represent it in this way and it definitely simplifies the equation. But for now, I'm going to just use what I did in the correction, just slightly changing it. So once we get to this equation, this was our original thing, A minus lambda I, and then this is our eigenvector V is equal to 0. So we set V as equal to xy. We put that in. Make sure we keep our golden ratio rather than the actual thing. And we set this to be 0, 0. And we get two equations when we do this. 1 minus x plus y is equal to 0, and x minus golden ratio y is equal to 0. So for property 1, we substitute property 2 into this. So like property 2, we can say that x is equal to the golden ratio y. We sub 2 into 1, we get this equation. And then we put this into the front, so then we arrange it to this form, and we see that this is equal to 0. So then our y could be technically anything. So then it wouldn't matter. So then we just set y equal to 1. X would just then be the golden ratio. So then our v would just be the golden ratio 1. And then it's the same logic for lambda equals the other variable. So then we would get that v is equal to this thing. And then inside part E, what we do is, let's see the question first. Compute a non-singular matrix P and a diagonal matrix D such that A is equal to P of negative inverse dP. Okay, so we want to find the non-singular matrix and diagonalize it. Okay, so that's pretty straightforward, I'd say. I know what to do, but because I didn't find the eigenvector in the test, I was unable to do this question, but I outline what I've done. Here is probably the correct steps as well. Just for my own liking, I set P is equal to V inverse, so then I would just get it to like the usual form that I like, just because I don't usually like the inverse in front. So then I know that inside here, because I already calculated the eigenvalues from earlier, then I just put the eigenvalues in the diagonal matrix on the diagonals. That's pretty standardized. And then for my V inverse, I would just put in the eigenvectors at like that I found in part D as my column vectors. So it would be this and this. So these are my eigenvectors. And then next, I would try to find the inverse. So my inverse is V is equal to the inverse of that. So then I went to go find the determinant of this times the thing over here. I just swapped the thing and then inverted it. And that I got this form. So then I know that my AV is equal to lambda V. So that I would get A squared V is equal to A of V. So then I would just get lambda squared of V. So then that simplifies my calculation and I would be able to get it down to this form. So then I was able to write my thing as this would be my final thing. Okay, so I think Vincent had a better thing. I'll talk about what he did in here. Can't exactly remember what he did, but I'll definitely check on that. I'll store this and then I'll go back to this a little later. And the F used the previous parts to find a simple formula for Ln. This is worth 5 marks, but I don't think it's worth 5 marks, to be honest. I think it's worth maybe like 3 or 4 most. So we know that in part B we got to this form. And then I'd say the typical way of solving these type of things I would go with is like the A of n is equal to V D of n, V negative V inverse of that, and then just solve it that way. But I'd say a faster way here is to see that we can just split up this way so that it would be slightly, I'd say, easier. We just split up the 1, 2 to be our eigenvectors. So we can see that inside here when we write this, we see that C1 and C2 are both 1. So then we can write this essentially as A of n V1 plus A of n V2 by linearity. So then this is like the major breakthrough that makes it so much faster is to see that we can write 1, 2 using the eigenvectors. And because we can use the eigenvectors, we can just straight up change the A into the lambda because AV equals lambda V, right? That's the good part about eigenvectors. So then we can get it to this form. And then once we get it to this form, we know that, okay, yeah, we just plug back V1, V2, we get this combine it together, we get this. So then we get that out. We just extract the bottom thing and we get that Ln is equal to the two roots to the n power summed together. So that's pretty unique and nice. I'd say it's a really nice formula considering how if we were to do like the actual algebra bash, it would have been much more difficult than this. But I think the difficulty in this question is definitely for me, finding the eigenvector over here. I think that's still a difficulty. And then also just doing I think Vincent had a better way of doing this, but I think he basically used this property first before even going into the finding the inverse using this way. Okay, let's go into question 3. Question 3 is, I'd say by far the hardest out of the three questions. So let V be a vector space, let S equal to this. That's a subspace of V by linearly independent. Okay, so that's a good condition to have. And let W be inside of V. Suppose that V of each thing plus W is linearly dependent. Okay, so that's interesting. So like plussing one thing to everything turns it to dependent. Show that W is in the span of S. Um, yeah, W is in the span of S. Okay, so this part I'd say, yeah, 4 marks is reasonably allocated. So we just first write down the equation. What's really strike out to me is in the independent versus the dependent part here. Okay, so we just kind of think about, okay, what does it mean to be linearly dependent, right? If it's linearly dependent, then we must have some kind of C1 to Cn, which are coefficients. And then we must have a non-trivial solution that exists when we do this. Because it's guaranteed that, like, that's the definition of being linearly dependent, is that we have this thing over here must be one that's equal set to 0. It must have a solution. So then if we break down the sum, just break it down into CI, VI, and W, just extract W into the front because it's just a coefficient, then we would have CI, VI, and the sum of sigma CI is equal to 0. So then we can just break it down into two cases over here. Either this is equal to 0 or this is not equal to 0. If it's equal to 0, then the other thing over here, because it's equal to 0, must have been 0. But this can't be true since we are told that they're independent. So all C's must have been zero. So we have a contradiction over here because it can't be linearly independent if it's that way, right? Like it just can't. So then it has to be this case. So then we just set K to be equal to sigma of the CIs. So then substituting that back into the equation, we would just get that the W, just rearranging that, is equal to the sigma of negative CI divided by KVI. And since it's a linear combination, so it's in the span of S. I think that's the difficult part is definitely just like thinking of how to just directly using the dependent and independent conditions, and then lastly substituting K and breaking it into cases of like one is zero, one is not, to actually just say this argument, right? For this argument to hold. Part B, suppose that with respect to the standard basis, B is equal to the ma normal matrix, and then D is equal to this. The transformation of T from R squared to R squared is represented by the matrix. This, let B hat is equal to that, D hat is equal to that. Draw the arrow diagram, use a change of basis to represent T with respect to B hat and D hat. So 7 marks is allocated, which is very generous. And I say this is just bookwork. I wrote down the conditions over here, but this is not necessary. But the major thing over here is drawing this arrow diagram over here that I drew. Like, we do want to have the bases B and D hat on the top, and then the normal bases, like the original ones, on the bottom. We know that our P is to go from B hat to B, and the next our T is just from B to D, and then our S is from D to D hat. So that basically is just a roundabout way of doing T hat because we don't know what T hat is. So T hat is just basically when we do the thing is first P, so we have P here, then it's T, then T is here, and then last is S, and S is here. And we write down what we have here. Each of these are given. These are given. So everything here is given. B hat to B is really easy because B is standard. So it's just whatever it is. Whatever B hat is, B this map. This is exactly the same map. So we don't have to do much. The next, that's just basically restating it, just writing whatever it is here in the B hat, moving it over to P. Great, we're done the first step. And then T is, I think it was already given. Yeah, T was already given, so we just have to copy that matrix over and we're good. So T is this matrix that was already given. And then our last step, we're looking for the S. S is a bit more complicated, but I'd say it's thinking of how to represent um, D hat in terms of D. So then we'd have inside here we have inside D hat we have negative 1 0. Inside the first part it's 1 1 1 negative 1. So we want to have 1 and 1 to make this true because in order to get 1 1, which is over here, we would need in terms of D hat, because we're ending with D hat, so we have to express in terms of D hat. We would need something in the bottom to be 1. In order to create 1, we must have the second vector, we must have exactly one of it. So once that is determined, we know that we have 1 2 1. So in order to create the 2 to 1, you have to get one of the first one to do 2 minus 1 is equal to 1. So then that's why we have a 1 1 over here. And then the same rationale for getting 1 negative 1. 1 negative 1 can be 4 because we need a negative 1, it means that the second matrix must have been negative 1. So that's how we get the negative 1 over here. And then in order, because we have a negative 1, we have negative 2. To create negative 2 into 1, then we would need 3 of this. And it's also because this is negative, we would need it to be positive, so then we would have to do the negative 3 to create that positive. So that's why we have negative 3 over here. So then we just substitute what we have from before into this, and we just do matrix multiplication, and we get T hat is equal to this matrix. So I think this is pretty standard bookwork. Like there's nothing new about this. And and then the next question is say what it means for A, B, R of n times n to be similar. Okay, so similar basically means that for two matrices, A, B are similar if there exists an invertible matrix P such that B of P negative 1, A, P is like basically holds. So we have that exists. And it's basically the idea behind this is that it's the same linear map viewed from different bases. That's what similar matrices are. And for this question in the actual exam, it's like I know the definition, but I wrote too short of a statement, so then I lost half of the marks on it. But definitely, I should mention that P is invertible because you do need the inverse of that, right? And that's something that needs to be there, and it should be a sentence. So that's something I need to fix next time in my actual thing. And then the next question, the next part is just all like I lost all the marks basically in the section, but I think that's doable. It's not that challenging, but it is quite hard to understand what it's asking for. Okay, so assuming that A, B are similar. Okay, so that's our condition for all of them. Prove or disprove the following claims. Indeed, A, B are non-singular, A inverse and B inverse are similar. Okay, so we're given A, B are similar. So the answer is yes. Why is that the case? Because we know that A, B are similar, we can just write B as P inverse of A, P. And we know that when we try to invert something in the form of X, Y, Z inverse, it's going to be Z inverse, Y inverse, X inverse. So then it has to be swapped. So then our B inverse would just be this thing inversed. So then we would just have P inverse A inverse P. We get it to the form. Great, awesome. A is invertible. A inverse is invertible as well. Okay, great. We were able to solve part D. Part E asked us for any polynomial of this form, the matrix PA and PB are similar. Where for a matrix of X in R n times n, we define PX equal to this thing. So basically, it's just coefficient times first is the I, then is the x squared, so on and so forth. So what we do for this is we still start off with what we know, B is equal to P inverse AP. So that's the similar property we have. So we want to show that P of B is equal to P of A, like that thing. Yeah. So then we know that P of X is defined to be that expression, so each of that thing. So then we know that P of B is equal to this thing. Just plugged it in with the X with the B. Pretty straightforward. So then we can just plug in the definition of B into that thing, into the B. So then we would get this form. And then the major takeaway, like breakthrough, is to see that I could also be written in the same form of P inverse IP. So then we see that all of the terms have P inverse something P. So then we can extract that out by distributivity into the outer side. And we have C0I plus C1A, C2A squared, so on, so forth. And we see that, okay, great, this is just the definition of PA. So we get this to our desired form. So E is true. And then let's go with part F. A and the matrix A prime obtained from A by swapping two rows are similar. This is only 2 marks, so we know that it's probably not true. Like, honestly, so many are true that we have to be contradicting. So a really simple way by trial and error is just like either showing that it doesn't work or that, yeah, showing that it doesn't work. The case doesn't work. So, or several cases doesn't work. So then inside here, let's assume that A and A prime is swapping rows I, J. So it's not similar because similarity preserves the determinant. So when we swap two rows, essentially what we do is the determinant changes sign from positive to negative. So unless the determinant is zero, otherwise it's not equal. So then in any case, we would be able to find a one counterexample, and we would be able to say that it doesn't work out. And for part G, for some I, j in 1 to n. Let A prime prime be the matrix obtained from A by swapping rows I and j and swapping columns I and j. These matrix A and A prime are similar. Okay, this one is because from our last argument, if we swap two things, the sign would change. Yeah, and that wouldn't work out. But if we swap it twice, it's gonna cancel out and we should be fine. But why are we fine? Like we do have to actually show that, right? So we can essentially still think of the same idea. Earlier when we do the changing of the swap rows, it's essentially still multiplying it by a matrix, right? It's a Gaussian elimination technique. So then what we do here is we just think of it as our E as a matrix swap. So if we do it and put E in front of A, then we know that we're doing a row swap. And if we're doing E in the back, it's going to be a column swap. So then what we have is essentially A prime prime is just equal to EAE. So then we just do a row operation on the front and the row operation on the back. So then what that means is that if we know the definition of E, if we do a row swap and then do another row swap, it should be back. It's definitely reversible, right? So then we know that E of E is I. So E is just its inverse. So then A prime prime is just equal to E inverse of A of E. So then E is just our P. So then we get it to our desired form and it works out. I think the difficulty part with definitely D, E, F, G was that we didn't really do much of this inside class. And I think it would have been definitely helpful if we were able to do more examples and just think of how to switch between the matrix and how we get it to the desired form from P inverse B um, P to whatever form we need. And just substituting that, doing some algebra, finding some kind of property and seeing that, okay, we got the expression we need. I think that's the major takeaway from this. Um, yeah, I'll end it off here.